The combination of SHA-1 and RSA provides an effective digital signature scheme. Because of the strength of RSA, the recipient is assured that only the possessors of the matching private key can generate the signature. Because of the strength of SHA-1, the recipient is assured that no one else could generate a new message that matches the hash code, and hence the signature of the original message can be authenticated by the method. An alternative signature can be generated using a DSS and SHA-1. Although signatures normally are found attached to the message or file that they sign, this is not always the case. Detached signatures are supported. A detached signature may be stored and transmitted separately from the message it signs. This is useful in several contexts. A user may wish to maintain a separate message log of all messages sent or received. A detached signature of an unexecutable program can detect subsequent virus infections. Finally, detached signature can be used when more than one party must sign a document, such a legal contract. Each person's signature is independent and therefore it's applied only to the document. Otherwise, a signature would have to be nested with the second signer signing both the document and the first signature, and so on. Such a way, the PGP operation of authentication is going to get processed in this way. Next, we will move on to the second one, the PGP confidentiality, the PGP operation of confidentiality. How this PGP operation is going to provide the confidentiality for this particular message. So another basic service is nothing but this confidentiality, which is provided by encrypting message to the transmitter or to be stored locally as file. In both the cases, the symmetric encryption algorithm CAST128 may be used. Alternatively, IDEA or triple DES may be used. The 64-bit cipher feedback CFB mode is used over there. As always, one must address the problem of key distribution. In PGP, each symmetric key is used only once. That is, a new key is generated as a random 128-bit number for each message. Thus, although it is referred to in the documentation as a session key, it is in reality a one-time key because it is to be used only once. The session key is bound to the message and transmitted within it. To protect the key, it is encrypted with the receiver's public key as illustrated in the figure. Let's discuss about the figure, how it's going to be then. The generator or the sender generates a message and a random 128-bit number to be used as a session key for the particular messages. The message is encrypted using a CAST128 or IDEA or triple DES system with the session key. And the session key is encrypted with an RSA using an recipient public key and is appended to the message. The same thing has been concatenated over here, and that is going to be sent. The receiver uses an RSA algorithm with its private key to decrypt and recover the session key. The session key is then decrypted and that is going to be collecting the message from that. So such a way the confidentiality is going to be appended for this particular message. As an alternate to the use of RSA for the encryption, PGP provides an operation referred to as Diffie-Hellman. Diffie-Hellman is a key exchange algorithm. Already we have come across in the previous chapters. In fact, PGP uses a variant of Diffie-Hellman that provides encryption or decryption, as known as LGAML. Several observations may be made. First, to reduce encryption time, the combination of symmetric and public key encryption is used in this preference. To simply using an RSA or LGAML to encrypt the message directly, CAST128 and other symmetric algorithms are substantially faster than RSA or LGAML. Second, the use of this public key algorithm solves the session key distribution problem, because only the recipient is able to recover the session key that is bound to the message. Note that we do not need a session key exchange protocol of this type. because we are not beginning an ongoing session. Rather, each message is a one-time dependent event with its own key. Furthermore, given the store and forward nature of electronic mail, the use of handshaking to ensure that both sides have the same session key is not practical. Finally, the use of one-time symmetric key strengthens what is already a strong symmetric encryption approach. Only a small amount of plain text is encrypted with each key, and there is no relationship among the keys, thus to the extent that the public key algorithm is secure. The entire scheme is secure actually. To this end, the PGP provides the user with a range of key size options from 768 to 3072 bits. The DSS digital signature scheme key for signatures is limited to 1024 bits. Let's discuss about the third one, which is nothing but both services on the same message, confidentiality and authentication. This figure illustrates uh, illustrates both services may be used for the same message. First, a signature is generated for the plain text message and prepend to the message. Then the plain text message plus signature is encrypted using an CAST 128 or IDEA or 3DES, and the session key is encrypted using an RSA algorithm. This sequence is preferable to the opposite, encrypting the message and generating a signature for the encrypted message. It is generally more convenient to store a signature with a plain text version of a message. Furthermore, for purpose of third-party verification, if the signature is performed, first, a third party need to be concerned with the symmetric key when verifying the signature. So when both services are used, the sender first signs the message with its own private key, then encrypts the message with a session key, and finally encrypts the session key with the recipient's public key. Such a way, the both authentication and confidentiality together is going to be get provided with the particular process. Next, we move on to the next one, PGP compression. What actually PGP compression? A PGP compresses the message after applying the signature but both encryption. This is the benefit of saving space both for email transmission and for the file storage. The placement of this compression algorithm indicated by Z for compression and Z inverse for decompression. This signature is generated before compression for two reasons. One, it is preferable to sign an uncomposed message so that one can store only the uncompressed message together with the signature for future verification. If one signed a compressed document, when it would be necessary either to store a compressed version of the message for later verification or to recompress the message when verification is going to be required. Even if one were willing to generate dynamically a recompressed message for verification, a PGP compression algorithm represents a difficulty. This algorithm is not deterministic. Various implementations of this algorithm achieve different rates of in running speed versus compression ratio, and as a result produces different compression forms. However, this different forms, the different compression algorithms are interoperable because any version of the algorithm can correctly decompress the output of any other version. Applying the hash functions and signature after compression would constrain all PGP implementations to the same version of the compression algorithm. Second one, a message encryption is applied after compression to strengthen the cryptographic security because the compressed message has less redundancy than the original plain text. Cryptanalytic is more difficult. The compression algorithm used is zip, which is described later. We will see about that particular zip in the future.